Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the Nernst equation. In our previous classes, we have finished the how to calculate the cell potential using the hydrogen electrode and what is the hydrogen electrode and all these concepts we finished. Now, in today's class, we are going to discuss the Nernst equation. So, let us see how to use the Nernst equation. Nernst equation. The use of Nernst equation is it can be applied to the any type of the electrochemical cell at any given concentration. So let us take a reduction reaction for a particular metal electrode and apply the Nernst equation. The reduction reaction is a metal ion in aqueous state is taking n number of electrons and changes to the metal in solid state. So to this we shall apply the Nernst equation. So electrode potential, here metal ion is changes to the m metal, so that we can write down that n plus changes to the m is equals to E naught of same metal electrode standard reduction potential Mn plus by M minus RT divided by NF log concentration of products by concentration of reactants. Concentration of product is here metal in solid state and reactant is ion in aqueous form. And remember that concentration of solids always to be taken as 1. So here in this place we can write down the 1 and the equation now changes to the n plus by m is equals to E naught n plus by m minus RT by NF log 1 upon concentration of n plus m. Now let us try to change this equation to the base 10 logarithms. It is in the base E form. So multiply this above form with the 2.303. So equation can be written as Mn plus by m is equals to E naught Mn plus by m minus 2.303 RT by NF log 1 upon concentration of Mn plus. Here 2.303 R value, T value, F value, these are all constants. Now T value is not constant, T value depends. So here we can write down that R value is the universal gas constant 8.314 joules per Kelvin per mole, where T equals to temperature, that is at a given temperature. When temperature changes, everything changes. N equals to number of moles of electrons exchanged in the given reaction. F equals to Faraday, whose value approximately is equals to 96,500 coulombs. Now let us try to take these values 2.303 or again T values at a given temperature. The value of 2.303 RT by F. If you take the 0 degree centigrade, that means 273 kelvins of temperature. 2.303 is constant, R value constant, T value is 273 kelvins, F is 96,500 coulombs. Its value becomes equals to 0.054. If you take 5 degrees centigrade, that means 278 kelvins of temperature. This value becomes 0.055. If you take the 10 degrees centigrade, this value equals to 283 kelvins and it becomes 0.056. If you take 15 degrees centigrade, it is equals to 288 kelvins. This value equals 0.057. If you take the 20 degrees centigrade, this is equals to 293 kelvins, 0.058. If you take the 25 degrees centigrade, that is what we consider the room temperature. So this value equals to 298 kelvins in kelvins. The value equals 0.059. And you can take the 30 degrees centigrade also. Then it is equals to 303 kelvins. The value equals 0.06. So much difference is not there. Whichever temperature you take, usually we take these two temperatures. So that here it continues like this. We take this temperature at 298 Kelvin. So all calculations are going in by considering the temperature 298 kelvins. So, but now and then we take the 0.06 also. Why? Because the calculations becomes very easy. 0.06 with 0.06 compared to the 0.059. So now by substituting at 298 kelvins, the equation is reduced to, now in this place 2.303 RT by F place, I can write down the 0.059. So the equation changes to now E mn plus by m is equals to E naught of mn plus by m minus 0.059 by n into log 1 upon concentration of the given metal ion or electrolytic solution. So here we can write down the two type of the graphs. The above equation can also be written in another form also. That is E equals to E mn plus by m reduction potential and its E naught value, reduction potential value, plus 0.059 by n into log 1 mn plus concentration of mn plus. So by taking this one, it's a graph y equals to mx plus c form. So for this the graph is, if you draw a graph between the electrode potential of n plus by m by taking on y-axis, and on x-axis if you take the log 1 upon mn plus form, concentration of mn plus, then it is a minus slope, negative slope. So the graph comes like this. And this is the intercept value, which is value is equals to E naught mn plus by m, and slope is equals to minus 0.059 by n. And if you take this particular equation, y equals to mx plus c, so positive slope is there. So for this, now again E mn plus by m, here the graph is with respect to the log concentration of mn plus, so it gives the positive slope with intercept, so the graph comes like this. So this is the intercept value E naught mn plus by m, and this is the slope value. Slope is equals to 0.059 by n moles of electrons. Now let us try to use this Nernst equation and apply to the in galvanic cell both copper electrode as well as the zinc electrode. And while applying, we shall consider only the reduction reactions. We don't consider the oxidation reactions. We can consider oxidation also, but as per IUPAC convention, standard reduction potential means automatically it is a standard electrode potential means only reduction potentials are considered, and we consider the reduction potential. So we shall see that now. So Daniel cell electrode reactions, considering reduction reactions for both cathode and anode. So here cathode reaction. We already discussed the reduction reactions happening at the various electrodes in the Daniell cell. So that here cathode means a copper electrode undergoing the reduction Cu2 plus in aqueous form. Take up 2 electrons, deposits as the copper metal, applying the same Nernst equation at 298 kelvins. So E cell electrode potential of Cu2 plus by Cu is equals to E naught of Cu2 plus by Cu minus 2.303 RT by 2F. Why? Because 2 moles of electrons are involved here. So log 1 upon concentration of Cu2 plus in aqueous form, because copper is the solid that we are not considering now. Now anode. Anode reduction reaction. Actual oxidation reaction takes place at anode, but while calculating the here E naught part is there. In this area E naught is there. So when you apply completely to this cell reaction, E naught means E naught cathode minus E naught anode. Both are reduction reactions only. That's why we consider the reduction reaction for the anode as well. So for anode, Zn2 plus aqueous form take up 2 more electrons and changes to the zinc in solid state. So here E of Zn2 plus by zinc gives E naught of Zn2 plus by zinc minus 2.303 RT by 2F into log 1 upon concentration of Zn2 plus ions. Now let us combine these two equations. And apply it. So let us consider equation 1 and equation 2. So from equation 1 and 2, we know that E cell is equals to E cathode minus E anode. So what is E cathode? Cathode is this one. So from this equation we have to subtract this equation. That means E Cu2 plus by Cu minus E Zn2 plus by Zn. That means it becomes the E cell. Similarly, E naught of this value minus E naught of this value, so that it becomes the E naught cell. Minus 2.303 by 2F is common, so that we take the common. Log this value minus this value. So log A minus log B. Log A by B. So we get the equation 1 like this. For galvanic cell, E cell equals to E naught cell minus 2.303 RT by 2F log concentration of Zn2 plus divided by concentration of Cu2 plus. So by changing the sign convention, we can exchange those two numerator and denominator values, and finally it becomes the E cell is equals to E naught cell plus 2.303 RT by 2F log concentration of Cu2 plus divided by concentration of Zn2 plus at 298 kelvins. 298 kelvins means this entire formula becomes the 0.059, where 2 remains same. So now here we can write down that E cell is equals to E naught cell plus 0.059 by 2 into log concentration of Cu2 plus divided by concentration of Zn2 plus. So this is the equation for the Daniell cell. The question arises here is how to get the maximum potential from the galvanic cell or Daniell cell. So here E naught cell for a particular 2 electrodes remains same, 0.059 by 2 also constant. So this entire part remains constant. That means E cell value depends on these two concentrations. If you take the higher the concentration of the Cu2 plus ions, E cell value increases. If you take the lower the concentration of Zn2 plus ions, then again E cell value increases. Where these Cu2 plus ions are present, they are present in the cathode side. Zn2 plus ions are present on the anode side. That means higher the electrolyte concentration on the cathode, lower the concentration of the electrolyte in the anode, more electrode potential will be developed in the galvanic cell or any electrochemical cell. So concentration of cathode electrolyte must be higher and concentration of the anode electrolyte must be lower. So that we shall write down that higher the concentration of electrolyte in cathode and lower the concentration of electrolyte in anode, more the EMF of cell. So without solving questions only we can easily identify in which case more potential is developed, so that you have to compare the concentrations of the both electrolytic solutions. So if this criteria is fulfilled, then automatically such a cell will produce the more quantity of the electrode potential. So now let us try to see how this Nernst equation is applied to the general equations. So let us take another example. Nickel by Ni2 plus solid aqueous form, double vertical line, silver ion by silver metal. So if you want to apply Nernst equation to this type of the equations, you must see that these two charges must be same. If charges are not same, then what is to be done? Use this number to multiply this value. So that this entire half part has to be multiplied with 2. So it becomes 2Ag plus. There are some questions where here 2 shall be there, here 3 shall be there. Means both are different numbers. One is odd number, one is even number is present. Then with this number multiply that half reaction, and with that number you multiply this half reaction. So that I will show you how to get this equation. See, if you write down the oxidation reaction for this, nickel changes to the Ni2 plus aqueous form and releasing the 2 electrons, and Ag plus their cathode reduction reaction in aqueous form taking up that electron and changes to the silver solid. But here electrons are not equal. In a particular reduction reaction, redox reaction, the number of electrons must be same for both oxidation reaction as well as the reduction reaction, because whatever the number of electrons lost in the oxidation reaction must gain by the reduction reaction. Otherwise such reaction do not complete. So here we have to multiply this equation to make these electrons equals to that electron. So then 2 electrons cancel out. Solids not required for us because their concentrations are taken as 1. So 2Ag plus in aqueous form gives Ni2 plus in aqueous form. This is what I said. So that multiply this part with a 2 number. So that here you got the 2. Then applying the Nernst equation to this, E cell is equals to E naught cell minus 0.059 by 2 electrons. See, I am considering all these conditions at the 298 Kelvin, so that 0.059 I am considering here. Log concentration of product by concentration of reactant. Product is Ni2 plus. Reactant is Ag. How many are there? 2 are there. So concentration of Ag plus whole square. Now let us take another example. Example number 2. Similar, but I am taking now, instead of this one, we shall take the magnesium. Mg by Mg2 plus Ag plus by Ag. Again, numbers are different. So multiply this part with this number. then automatically it becomes 2Ag plus. And without writing this type of the equations, now how to write down directly this equation? Very simple. In this particular half reaction, this is the reactant, this is the product. In this half reaction, this is the reactant, this is the product. See, reactants are in solid state here, here product is solid state. According to the Nernst equation, concentration of product by concentration of reactants. So E cell is equals to here E naught cell minus, let us take 298 Kelvin's temperature, 0.059. How many moles of electrons means higher the charge? So 2 moles of electrons. Here it is lower charge. Only one is there. Or else if different numbers are there. So it, for example, here 3 is there. 3 into 2, this is, and here this has to be multiplied with 2. This has to be multiplied with 3. So total number of electrons exchanged will be equals to 6. So then n value will become this 6. But in this case, it is equals to only 2. So 2 log concentration of product. What is the product here in this entire remaining ions? This is the product. So concentration of Mg2 plus by, which is the reactant, concentration of Ag plus. But this has to be multiplied with the 2, no? So then automatically we'll get the 2. But while writing the equation, we don't write the stoichiometric coefficients while representing the cell representation. But while writing the Nernst equation, we take the stoichiometric coefficients. Why? Because Nernst equation main criteria is to explain the EMF value in terms of the concentration. When stoichiometric coefficient changes, automatically concentration values also changes. That is the reason why here we take the stoichiometric coefficients. That's why I multiplied here. But while representing this, you should not represent. So that I'll arrange this part here. So one must be careful while writing this type of equations without writing like this. Why? Because you will forget the stoichiometric coefficients. So in rough side, you write down this equation and multiply and complete that and automatically go for this equation. What if the reaction is given in a general way? Very general way. Let us take A plus B gives C plus D. Nothing is solid. All are either in the aqueous form or ions, whatever it may be. So in such cases, E cell is equals to E naught cell minus 2.303 RT by, let us consider n moles of electrons exchanged. So I am taking n electrons. Then log concentration of products by concentration of reactants. Concentration of products along with their stoichiometric coefficients divided by concentration of reactants along with their stoichiometric coefficients. So this is the way to write down the Nernst equation.